In this next section, we'll look at the flash data layout. The question we're asking here is, how is the data organized and laid out on individual SSDs? XtremIO uses a fixed block layout. That is, the data is written out in RAID stripes, a RAID set of 23 plus 2 disks. Once a drive is fully written, partial stripes are updated in place with the new data. The benefit here is that existing data doesn't move once it's written. The blocks, as they're laid out, are a fixed 8K size. This means that they can be easily reused. One question to ask is, what does the size of those blocks need to be? In the case of XtremIO, it was originally a 4K block, which helped significantly with dedupe performance. In a recent software update, the block size was changed to 8K to better be efficient with the amount of space and the amount of RAM that the metadata was taking up. In contrast, SolidFire and Pure use a log-structured file system. In this solution, the SSD space is divided into fixed-size segments, in the case of SolidFire 1 meg in size. Incoming data is aggregated into segments and then written sequentially into these segments. Once a drive is fully written, any partial segments or segments that are no longer completely full with data are recycled during garbage collection, re-aggregated, and written to a new location on the disk. The benefit here is that individual blocks can be variably sized. There's no requirement for a 4K or 8K fixed block size. It's important to know why the flash data layout matters. The easiest way to do this is to look at the performance of a standard commercial SSD. For these tests, we set up different types of writes to the drive, and then we measured how many read I/O the drive would support at the same time. If we use 128K random writes, meaning small bytes that are written across the drive randomly, you see the quick fall off in read performance as the disk fills up and garbage collection is run. Once everything settles out, we see about 2,500 read I/Os with a pretty rough variable latency profile. If we take that exact same drive and we use a much larger 1 meg random write profile, we see that the read performance gets much better, up to around 9,000 IOPS, but the latency is pretty terrible. Well, what if we combine the two? What if we take the larger write size, but instead of randomly writing it across the SSD, we make it sequential? When we do this, we hit the sweet spot that makes log-structured file systems so well suited for all-flash arrays. We get almost double the read performance, up to 17,000 IOPS, and we get an almost perfect, consistent latency profile. Looking at this, you might ask why it is that XtremIO decided to go with a location-addressed model. Why is it that XtremIO isn't using a garbage collection process at the system level? The secret here is in the drive that was originally used. There was a company called Anobit, and they made an incredible SSD. As you can see here, even with 128K random writes, one profile that would kill a normal drive, the read performance and latency profile of the drives was amazing. With a drive like this, why bother doing a log-structured design at all? Of course, there was also a bit of a challenge when Apple bought Anobit, forcing XtremIO to find another drive with similar performance, but they were certainly able to do that. In summary, we have two ways to solve this problem. On the fixed block side, the biggest difficulty is the inability to support variable size blocks. We also see a lot of write fragmenting, that is, taking large writes and fragmenting them into multiple 4K writes before they hit the SSD. In this solution, the SSD controller itself does the flash page management, which generally requires more SSD over-provisioning. In the case of eMLC drives, that's usually about 28%. This solution is best for simpler file systems, especially when those eMLC SSDs are available. On the log-structured side, we see easy support for variable size blocks, which makes features like compression very easy to implement. We also see write coalescing, where we take lots of small writes that we concatenate into large writes before we send them to the SSD, which helps with driveware management. The storage system itself helps with the flash page management rather than the SSD, which means that we need much less over-provisioning, usually around 7%. This solution is going to be best for environments where CMLC SSDs are being used to lower the cost of the solution, and environments where compression support is required.